Welcome to our series on gases, and today we're going to look at diffusion. So what is diffusion? Diffusion is the ability of a gas to spread out and completely fill its container. This is due to the natural movement of particles called Brownian motion. The movement of particles from regions of higher concentration to lower concentration can also be used to describe diffusion. Eventually, all these particles will disperse evenly throughout space. So here I have a picture to try and help illustrate what diffusion is. In the first container I have two gases, one marked by the clear circles and the second by the shaded circles. I can see my second gas here is in high concentration at the bottom of the container, and this is prior to diffusion. If we compare that to the second container, which is after diffusion, we notice how the shaded circles have spread out evenly through the container and mixed with that second gas. So this should give you an idea of what diffusion is. So let's look at the density of gases. We often don't think of gases as having density, but they do, and different gases have different density. To try and illustrate that, I sometimes consider two balloons, maybe one filled with helium and another filled with oxygen, and try to consider, well, which balloon relative to each other would be more dense. So the first question I have to ask myself is, what is density? And density is equal to mass over volume. Let's assume that both of my balloons have the same volume. Their density then is going to depend on their mass. How do I work out the mass? Well, I go to the periodic table. And helium, the mass of helium is 4 grams per mole. The mass of oxygen would be, because it exists as O2, so that would be 32 grams per mole. So we can see from those calculations then that the density of oxygen will be much, much greater than that of helium. So compared to each other, oxygen is much more dense than helium. If I have these two balloons and I have them in our atmosphere, which is made of air, which will float, which will sink? Will they both float? Will they both sink? So we have to consider, again, the density of the gases. Helium is less dense than air, meaning the helium balloon will float. It will try and float above the air because the least dense ones will rise. Oxygen, on the other hand, is just slightly more dense than air, so it will lie on the ground. Now, what would happen if I had gases, say, leaking out of a balloon, and this balloon was filled with a mixture of gases, such as helium, oxygen, and nitrogen? How would these gases escape the balloon, and in what order? Well, helium, remember, has a mass of 4 grams per mole, so it would be quite light. Nitrogen, 28 grams per mole, and oxygen, 32 grams per mole. So the lighter gas will leave the fastest, followed by the next lightest gas, which would be nitrogen, and then followed lastly by the heaviest, which in this case was oxygen. So this brings us to Graham's law of diffusion. And this law states that the rate of diffusion, which is the volume escaping per unit time, is inversely proportional to the square root of the density of gas, provided the pressure and the temperature are kept constant. So this mathematically would be written that rate is proportional to 1 over the square root of the density. So for two gases, you would write it as follows. Or A, which is rate A, divided by or B, which is rate B, is equal to the square root of the density of B divided by the square root of the density of A. So look at this inverse relationship between or A and dA and or B and dB. So here I have the same equation that you've just seen, only I've replaced A and B with 1 and 2. Again, I would say pay close attention to that relationship between your rate and your density, the fact that they are inversely proportional to each other. Another interesting relationship is that density is proportional, not inversely proportional, but proportional to the relative formula weight, or prefer to call it the molecular mass. Density is also proportional to time. So from that, we can put together a number of useful equations. I can have rate 1 over rate 2 is equal to the square root of molecular mass 2 divided by the square root of molecular mass 1, which can be equal to time 2 divided by time 1. From a practical sense, what we're looking at here is that Graham's law is about smaller molecules being able to travel faster than larger molecules. Let's look at a worked example. A sample of an unknown gas flows through a wall of a porous cup in 39.9 minutes. An equal volume of gaseous hydrogen, H2, measured at the same temperature and pressure, flows through in 9.75 minutes. What is the molar mass of the unknown gas? So it wants me to find molar mass, and it has given me time, 9.75 minutes for hydrogen gas and 39.9 minutes for the unknown gas. Can I work out the molar mass of H2? Yes, I can. It's hydrogen, so its molar mass will be 2 grams per mole. So I have a pair there, 9.75 time, and I have a molar mass for the H2, which is 2. I have a second time, 39.9 minutes, and I have X as my molar mass for it. So putting that information together, I have time 1, which was my 39.9 minutes, and that was related to mass, molar mass of 1, which was X grams per mole. We don't know what that is. Time 2, we were given at 9.75 minutes, and mass 2 we do know, which is hydrogen H2, which gives us 2 grams per mole as its molecular mass. And we simply filled that data into the formula. So I end up at 39.9 divided by 9.75 is equal to the square root of X divided by the square root of 2. I then transpose that formula so that I end up with root X on its own as my unknown and all my knowns to the other side. When I put those knowns into the calculator, I end up with 5.78 is equal to the square root of X. But remember, I don't want the square root of X. I want X. In order to get X, I must square both sides. When I do that, I end up at 5.78 squared is equal to X, and 5.78 squared gives me 33.49, and that's equal to X. Again, let's check and see if our answer is reasonable. Remember, light gases travel very fast. So here I have 2 grams per mole, which was my hydrogen, and it travelled at a time of 9.75 minutes. My second sample was much slower. That would indicate that it's a heavier gas. Now let's check its molar mass, and it should be heavier than 2 grams per mole, and my answer turned out to be 33.49. So yes, it's heavier, and therefore I know my answer is reasonable. Let's have a look at another worked example. A fixed volume of oxygen, which exists as O2, diffused in 84.8 seconds. An equal volume of gas X took 120 seconds to diffuse. Calculate the molecular mass of X. So we're going to expect an answer of 64 here. So let's have a look and see what we're dealing with. We're dealing with seconds, so we're dealing with time, and we're also dealing with molecular mass. Can I calculate the molecular mass of oxygen? Yes, if I look it up on our periodic table, it's oxygen, but it's 2 oxygens. So it will be 32 will be the molecular mass of oxygen. And I'm looking to find the molecular mass of X. So in this instance, we have T1 divided by T2, which is time 1 over time 2, is equal to the square root of M1 divided by the square root of M2, which is the molecular mass of 1 and the molecular mass of 2. I then have to decide on my pairings, which ones I'm going to call T1 and M1, and which set of data I'm going to call T2 and M2. So remember, the oxygen and the 84.8 seconds is going to be one pair, and your 120 seconds and your x is going to be the second pair. So it's up to you to decide which ones you're going to call set 1 and which you decide to call set 2. So for set 1, I'm going to use my 84.8 seconds as T1 and my 32 grams per mole as my M1. So that was for my oxygen. For T2, I'm going to have 120 seconds and I'm going to have my X grams per mole because it's M2 is what I'm looking to work out. When I fill that data into the equation, I end up with 84.8 divided by 120 is equal to the square root of 32 divided by the square root of X. Now you'll notice in this example compared to the last one that the square root of X is actually on the bottom of the fraction as opposed to the top. The reason being was because of how I chose my pairs, whether I labeled them as 1 or 2. In this instance, I labeled them as 2, so my X is on the bottom. Had I chosen to label that pair as 1, then my X would have been on top. It doesn't really matter which one you label, 1 or 2. The most important thing that you do is that your X is always brought on top. Now you can transpose this equation so that X ends up on top. However, there is a shortcut, and that shortcut is that you flip both fractions. If I flip both fractions, I end up with 120 now on top divided by 84.8 is equal to the square root of X, which is now on top, divided by the square root of 32. I'm now going to transpose that equation so that I get the square root of X on its own and all my knowns to the other side. When I do this, I have 120 multiplied by the square root of 32 divided by 84.8 is equal to the square root of X. When I put that into my calculator, I end up with 8 is equal to the square root of X. Now remember, you're not finished at this point. We don't want the square root of X. I want X. In order to get rid of the square root, I must square both sides. When I do this, I end up with 8 squared is equal to X. When I square 8, that becomes 64. So 64 is equal to X. The next thing I need to check is that my answer is reasonable. So let's have a look and see. So at time 1, which is 84.8 seconds, I had a molecular mass of 32 grams per mole. At 120 seconds, which is a slower time, compared to the 84.8, so therefore I would expect a larger molecular mass. I have 32 for my oxygen, and for my M2, I got an answer of 64, which is larger than 32, so therefore my answer is reasonable. I want you to have a go at this one yourself. Let's have a look. A volume of 5 centimeters cubed of sulfur dioxide diffuses through a porous plug in 1 second. So just to be aware that this is distance and time. Distance over time is rate. So now you're looking at rate. What volume of methane would diffuse through the same plug in 1 second under the same conditions? Okay, so I'm looking to find rate. What other information do I have? Do I have time? No. Do I have density values? No. But what I do have is the formula here. I have methane, which I know is CH4, and I have sulfur dioxide, which I know is SO2. And what I can do with these is calculate the molecular mass. Sulfur is 32, oxygen is 16, and I've got 2 of those. I also have carbon here, which is 12, and hydrogen, which is 1, but I have 4 of them. So I can calculate the molecular mass for these. So now we're looking at rate and molecular mass. So go back and have a look at the formula that has a relationship between rate and molecular mass, fill in the data, and see how you get on. The answer should be 10 centimeters cubed per second as your second rate that you were looking to work out. The answer then is given on the following slide, so pause this video and see how you get on. So here is the calculation breakdown for that problem. The equation you should have chosen was rate 1 divided by rate 2 is equal to the square root of the molecular mass 2 divided by the square root of the molecular mass of 1. If you didn't get the answer of x is equal to 10 centimeters cubed per second, I would suggest you go back and have a look at your pairing. So the pairing should have been x, the one you're looking for, centimeters cubed per second, and that should have been paired with your 16 grams per mole, which was for your methane. The second pairing would have been your 5 centimeters cubed per second with your 64 grams per mole, which was for your sulfur dioxide. Now, which one you call R1 and M1 and R2, M2 as a pair really doesn't matter, provided the X and the 16 are linked as a pair and the 5 and the 64 are linked as a pair. So try that if you had a problem. Here's one last one for you to have a go at, and it says carbon dioxide, CO2, diffuses through a hole at a rate of 16 centimeters cubed per second, while another gas, X, diffuses through the same hole at 8 centimeters cubed per second. Calculate the molecular mass of X. So now we're looking again at rate and we're looking at molecular mass. The answer you should get for this is 176 grams per mole. As ever, the calculation breakdown will be on the next slide, but pause the video and try it yourselves first. So here's the calculation breakdown for that, and as you can see, X is equal to 176 grams per mole. So that's all we're going to have a look at today for diffusion. In the next presentation, we are going to look at Dalton's law of partial pressure. Thank you very much for listening.